You know the exact scenario I'm about to describe because, well, it is a universally shared human experience.
Oh, yeah. I think we all know where this is going.
Right, so it usually happens late at night, the house is quiet, the television is on in the background, or maybe, you've just wrapped up an incredibly stressful day at work.
Yeah, your brain just feels like it has been put through a blender at that point.
Exactly. So you walk into the kitchen, you open the pantry, and there it is.
The target.
The Target. That brightly colored bag of highly processed snacks. I mean, maybe it's potato chips, maybe it's those perfectly engineered little chocolate-covered pretzels, or, a sleeve of cookies.
Oh, it's always the cookies for me.
Right. And you stand there and you tell yourself with absolute unshakable conviction, I am just going to have a handful.
Just a taste.
Just one cookie to take the edge off.
And it's the ultimate rationalization, isn't it? We fully believe our own lie in that specific moment.
We really do. We believe it every time. So you reach in, you take that handful, you close the bag. Maybe you even put a little plastic clip on it to, seal the deal.
To make it official.
Right. And you walk away. You sit back down on the couch. But then, 10 minutes later, a thought creeps in.
Just one more.
Yeah. You are back in the kitchen, and then 20 minutes later, you're back again. The clip comes off, the clip goes on.
Over and over.
And before you know it, you're staring down into a completely empty bag.
It's the worst feeling.
It is. You are surrounded by crumbs, staring at the shiny foil interior, and suddenly this profound, crushing sense of guilt just washes over you.
Yeah, you start questioning everything.
Exactly. You think, what is wrong with me? Why do I have zero willpower? I'm a grown adult. Why can I not control my own hands?
Right.
And every single person listening right now knows exactly what that specific loss of control feels like. It feels like a moral failure.
It really does.
Yeah.
But what if we told you that it's not?
Exactly. What if I told you that this isn't a personal failing at all? What if this has absolutely nothing to do with your willpower?
Which is a wild concept to accept.
It is. But you have basically just been the victim of a literal biological hijacking. And it's taking place deep inside the ancient structures of your brain.
And, it completely changes the paradigm when you look at it through that lens.
Totally.
Because we spend so much of our lives and so much of our cultural energy moralizing our food choices.
Absolutely. Good foods and bad foods.
Right. We label foods as good or bad, and by extension, we basically label ourselves as good or bad, depending on what we consume.
Yeah, it was bad today, I ate a donut.
Exactly. But the underlying mechanics driving that late-night pantry raid, they're purely, ruthlessly chemical.
Which is just fascinating. So welcome to the deep dive. Our mission today is to completely unpack a specific silent group of brain chemicals that are secretly pulling the strings on our impulsive eating habits.
And pulling them very effectively, I might add.
Very effectively. We've been poring over the latest research focused on the science of human performance, longevity, disease prevention, all that stuff.
Really cutting-edge data.
Right. And hidden within all this data is the introduction of our main antagonist for today's discussion. They are a family of peptides called dynorphins.
Right.
That is spelled Dynorphins, dynorphins. And they influence our eating habits in ways that are, quite frankly, a little terrifying.
They really are.
Especially when we start talking about how they interact with modern junk food.
Well, what's fascinating here is that the moment you understand dynorphins, you completely stop blaming yourself for that empty bag of chips.
You really do.
Because we are talking about a critical component of the brain's deeply ingrained reward and survival circuitry.
It's ancient hardware.
Exactly. And what the latest neurological mapping reveals is that modern ultra-processed food hasn't just accidentally stumbled upon a recipe that tastes good to us.
Right. It's not just a happy accident.
No, the food industry has fundamentally learned how to exploit the specific chemical pathway.
It's engineered.
Heavily engineered. So when we understand how dynorphins operate on a cellular level, we can finally strip away that heavy, useless guilt.
Which is so freeing.
It is. We can step back, pop the hood on our own biological machinery, and analyze the problem objectively.
So, okay, let's pop the hood.
Let's do it.
If we want to understand how these dynorphins are hijacking our brains, we first need to figure out exactly how and where they are operating.
Right, we need the map.
Yeah, we need to go from this abstract concept of a chemical peptide just floating around in the ether to the actual biological geography of our minds.
Because they don't just float randomly.
Right. Dynorphins don't just wash over the brain like a wave, hoping to bump into something and cause a reaction. They have very specific targets.
Or highly specific.
Yeah.
I mean, you can think of the brain as having millions of microscopic locks on the surface of its cells.
Okay, locks. Got it.
And dynorphins are a very specific master key for certain locks.
Mm.
They latch onto a specific type called a kappa opioid receptor,
Okay.
or a KR for short.
Kappa opioid receptors. I want to linger on that for a second.
Sure. Yeah.
Because people hear the word opioid and they immediately think of, prescription painkillers or illicit drugs.
Right, the heavy stuff.
Yeah. But we are talking about endogenous opioids here, like chemicals our own bodies produce naturally.
Exactly. Our bodies actually produce several types of natural opioids to manage pain, stress, and reward.
Like endorphins, right?
Yes, most people have heard of endorphins. Those are the feel-good endogenous opioids.
A runner's high.
Precisely. You go for a long run, your body releases endorphins, they bind to their specific receptors, and you feel that famous runner's high.
Okay, so where do dynorphins fit into that?
Well, dynorphins are part of that same broad family, but they are sort of like the dark mirror image of endorphins.
Oh, wow. The dark mirror image.
Yeah, and they are the ones that bind specifically to the kappa opioid receptors, the KRs.
Okay, so where exactly are these KR locks located? Like, are they just evenly distributed throughout all the brain tissue?
No, and that is actually the critical piece of the puzzle. While you can find them in various places, they are heavily concentrated and tightly clustered in specific control centers,
Which centers?
the ones responsible for feeding behavior and reward processing.
Oh, so they're literally stationed where we make food choices.
Exactly. We are talking about areas like the hypothalamus, which acts as the body's ultimate command center for basic survival functions,
Okay.
and the nucleus accumbens, which is essentially the brain's pleasure and reward hub. So these KOR docking stations are stationed precisely in the biological real estate that dictates when we eat, why we eat, and how we feel about what we are eating.
Which means that clustering in the hypothalamus and the reward centers is definitely no accident.
Not at all.
There was actually a fascinating piece of research recently that really demonstrated the raw, unadulterated power of these chemicals.
The mammalian injection study.
Yes. So researchers wanted to isolate exactly what dynorphins do, right? So they took specific synthetic dynorphins and injected them directly into the brains of mammals.
Which is an intense procedure.
Very. And normally, if you take a powerful neurochemical and just dump it directly into a mammalian brain, you would expect a whole cascade of chaotic reactions.
Oh, you would absolutely expect a generalized systemic response.
Yeah, like the whole system going haywire.
Exactly. Like if you inject dopamine or adrenaline, you might see hyperactivity, elevated heart rate, erratic movement.
Maybe sudden changes in sleep patterns.
Right. Or a massive fight-or-flight response.
Yeah.
You expect the animal's entire behavioral state to shift dramatically.
But that is not what happened here.
No, it wasn't.
When they injected the dynorphins into these mammals, they didn't start pacing around frantically. They didn't suddenly fall asleep.
Their heart rates didn't explode.
Right. The only behavioral change, like the single isolated result, was that the mammals immediately started to eat.
And eat, and eat.
Yes. A massive immediate trigger of pure appetite.
It's incredible because it isolated the feeding behavior completely from every other mammalian function.
It just bypassed everything else.
Totally. It bypassed the stomach,
Yeah.
it bypassed the normal hormonal hunger cues, and went straight to the behavioral output. Eat now.
I was actually trying to visualize how bizarre this is, because I think a lot of people imagine brain chemistry like a universal remote control for a television.
Okay, yeah.
You press a button and it sends a signal that does a dozen things at once. It turns on the TV, it boots up the surround sound system, it dims the smart lights in the living room.
Maybe it turns up the thermostat, too.
Right, it triggers this holistic environmental shift.
Right.
But the way dynorphins interact with those KRRs, it is more like finding a highly specialized remote control hidden under the couch cushions.
A secret remote?
Yeah. And this remote only has one single giant red button on it.
And nothing else.
Nothing else. And when you press that button, it doesn't touch the lights, the sound, or the temperature. It doesn't do anything else in the entire house except trigger this overwhelming singular directive.
Consume food.
Consume food. But okay, let's unpack this. Biologically speaking, why would the brain evolve such an isolated, incredibly powerful trigger that does literally nothing but force you to eat?
Well, to understand the why, we really have to travel back a few 100,000 years.
Okay, back to the ancestors.
Exactly. We have to look at the ancestral environment in which the human brain evolved. From an evolutionary standpoint, finding and consuming calories is the single most critical, difficult, and dangerous behavior for a mammal to successfully execute in the wild.
Right, because in the wild, the default state is basically starvation.
Precisely.
Mm.
For the vast majority of human history, food was not guaranteed.
You didn't just have a fridge.
Right. You didn't know if your next meal was coming tomorrow, next week, or next month.
Winter approaches, crops die.
Animal herds migrate away.
Mhm.
Starvation was just a constant looming threat. And because finding food is so critical, the brain cannot afford to rely on just one simple mechanism to make you hungry.
It needs backups.
The data actually shows that different parts of the dynorphin molecule and various subtypes of dynorphins can all independently stimulate this appetite.
Wait, really?
Yes, and this redundancy is the key. It reveals that the brain has essentially built a fail-safe backup system.
So we have our primary hunger systems, things like the hormone ghrelin, which makes your stomach rumble when it's empty,
Right.
or leptin, which tells you when you have enough fat stored.
Exactly.
But dynorphins are something else entirely.
Dynorphins are the emergency override.
The big red button.
Imagine a scenario where a hunter-gatherer is exhausted, stressed, maybe a little sick,
Okay.
and the primary hunger cues are being suppressed by cortisol and adrenaline. The body is in danger of starving, but the normal signals just aren't getting through.
The brain is ignoring the empty stomach.
Right, so the brain detects this critical energy deficit and slams that giant red button. It floods the KORs with dynorphins.
Wow.
It is an emergency protocol designed to bypass everything else and make absolutely sure you forage and eat, regardless of how tired or stressed you are.
It forces you to move and find calories.
In a harsh natural environment where food is scarce, having a specialized, overriding chemical drive that forces you to consume calories could literally be the difference between life and death.
Okay, so we are walking around today, right now, carrying this ancient fail-safe survival mechanism in our heads.
We are.
And it's a beautifully designed system for a world of famine and scarcity.
A perfect system for that world.
But let's extrapolate this into our current reality. What happens when you take this famine response backup system and you drop it into the modern world?
It's a disaster.
Because we are navigating an environment that is quite literally overflowing with easily accessible, calorie-dense, ultra-processed foods.
Everywhere you look.
You can't even buy gas for your car without walking past a massive wall of engineered snacks.
Right. It becomes what evolutionary biologists call an evolutionary mismatch.
An evolutionary mismatch.
And in this case, it is a mismatch of catastrophic proportions. The external environment has completely transformed in the blink of an eye, historically speaking anyway.
Right.
But the biological machinery inside our skulls hasn't changed at all. We still have the brains of hunter-gatherers.
So our brains don't actually know what a drive-through is.
They have absolutely no concept of it. So when we consume these hyper-palatable, heavily processed foods, we are continuously triggering a survival system that was designed for rare emergencies.
We're pressing the red button every day.
Multiple times a day. The dynorphins are doing exactly what they evolved to do over hundreds of thousands of years, but they are doing it in a context of hyperabundance.
Which turns a life-saving evolutionary adaptation into a profound modern liability.
Exactly.
It is doing its job way too well, and the food industry is just endlessly providing the ammunition.
They are.
But here is where the research takes a very sharp, very unexpected turn.
Oh yeah, this is the crazy part.
Because if dynorphins were just about making us hungry, like if they just pressed the eat button, that would be one thing.
Right.
That would be a straightforward, simple story of appetite. But what happens to the body once the food is actually consumed?
That's the real question.
The science goes from just talking about appetite generation right into the microscopic mechanisms of how the body manages energy.
The metabolism side.
Yeah, and there is an experiment involving genetic engineering that honestly broke my fundamental understanding of basic dieting.
You were talking about the knockout mice study?
Yes.
It is a brilliant and highly illuminating piece of biological research.
It is wild. So let me lay out what they did for the listener.
Sure.
Researchers bred what they call knockout mice. And for anyone unfamiliar with the term, this means the scientists went into the genetic code of these mice and selectively knocked out or deactivated a specific gene.
They turn it off.
Right. And in this case, they deactivated the gene responsible for producing dynorphins. So these specific mice physically cannot produce any dynorphins at all. Their bodies and brains are entirely dynorphin-free zones.
Blank slates in that regard.
Then they took these knockout mice, alongside a control group of regular mice, and they fed both groups a high-fat diet.
And it's worth noting, the researchers specifically designed this high-fat diet to perfectly mimic the macronutrient profile of the highly processed options that are so incredibly popular in today's human diet.
Wow.
So they're effectively feeding these mice the equivalent of a modern, continuous fast food diet.
Okay, right. So you have normal mice and you have dynorphin-free mice, both eating basically junk food.
Yes.
Now, common sense would tell you that without the dynorphins, without that giant red consume food button being pressed in their brains, these knockout mice would be protected from weight gain, right?
That's what you'd think.
Because they don't have the chemical driving them to overeat.
That was the initial hypothesis, yes. Without the appetite-stimulating peptide, they should theoretically consume less and remain leaner than the control group.
But the shocking result was the exact opposite.
Complete opposite.
These knockout mice, the ones completely lacking dynorphins, ended up getting significantly heavier than the normal mice.
Much heavier.
And here is the kicker, the detail that made me stop and reread the data like 3 times. They gained all this massive extra weight despite eating the exact same amount of food as the normal mice.
Same amount of food.
And in some measured cases, the knockout mice were actually eating less food than the control group, but they were still rapidly gaining more weight.
It represents a fascinating, almost unbelievable biological paradox.
I have to push back on this, or at least play the voice of the listener here, who is probably screaming at their phone.
Go for it.
Because this goes against literally everything we have ever been taught about weight management.
It really does.
Wait a minute, hang on. Because the absolute golden rule of dieting, the unquestionable gospel that every fitness magazine, app, and nutritionist preaches is calories in, calories out.
Right.
The law of thermodynamics. Yes, the law of conservation of energy. If you burn more calories than you take in, you lose weight. If you take in fewer calories than your neighbor, you should weigh less than your neighbor.
In theory, yes.
So how on earth can a biological organism, even a mouse, eat less food but somehow gain more mass? Like, how does that not fundamentally violate the laws of physics?
It is a fantastic question, and it is the exact crux of why this research is upending the entire field of metabolic science.
Okay, explain this to me.
The simple answer is that physics isn't being violated, but our application of it has been far too simplistic.
How so?
That rigid rule of thermodynamics, the calories in, calories out equation, assumes a closed, highly predictable system. But a biological organism is not a simple closed furnace where you just shovel in coal and measure the heat.
It's not just a basic math equation.
No, it is an incredibly complex chemical processing plant. The calories in part of the equation is fixed. If you eat 100 calories, you ate 100 calories. But the calories out part of the equation is not a fixed static number. It fluctuates wildly based on a million microscopic decisions your body makes every second about how efficiently it chooses to use the energy it receives.
Okay, so how do the dynorphins play into that efficiency? Like, what are they doing?
Well, the research suggests that dynorphins don't just act as a behavioral signal to the brain saying go eat.
Okay.
They also act as metabolic signaling molecules for the rest of the body. They communicate with your cells, particularly your fat cells and your mitochondria.
Powerhouses of the cells.
Exactly. They actually help regulate your basal metabolic rate. Without dynorphins, the body loses a fundamental layer of communication that balances energy intake with energy expenditure.
Wait, so if dynorphins are the spark that starts the hunger fire, you're saying they are also the thermostat that controls how hot the fire burns.
Exactly. That's a great way to put it. When the body receives a massive influx of high-fat, high-calorie food, a normal metabolic system will try to upregulate energy expenditure to burn off some of the excess. It might increase core body temperature slightly, or increase spontaneous physical activity, things like fidgeting.
Just burning it off naturally.
Right. But when the knockout mice lost their dynorphins, their bodies became terribly functionally inefficient at managing the high-fat diet.
Because the thermostat was gone?
Because that specific signaling molecule was missing, yes. Their metabolic thermostat basically broke. Instead of turning up the furnace to burn the high-fat diet, the cells panicked.
They panicked.
The metabolism shifted entirely into storage mode. The body essentially said, I don't know what to do with this massive influx of fat because my manager is missing, so I am just going to hoard all of it.
Wow. So it extracted every possible microfraction of energy from the food and just locked it away as fat.
Yep, whereas a normal mouse might have burned off a portion of it as heat.
So that resulted in massive weight gain, even with restricted caloric intake.
Precisely.
Yeah.
The efficiency of nutrient partitioning was completely corrupted by the lack of dynorphin signaling.
This is huge. So, for you listening right now, if you have ever sat there pulling your hair out, feeling like your metabolism simply isn't playing by the rules.
Which is so common.
Right. Like if you have ever felt like you were eating the exact same salad or even eating strictly less than the person sitting next to you, but you are still gaining weight while they stay perfectly lean,
Yeah,
this research is validating your experience. It suggests that weight management is not a simple math problem of willpower and counting calories.
it really isn't.
There is a microscopic chemical manager dynorphin that is deeply involved in dictating how efficiently your individual cells use energy.
And this manager is heavily, drastically influenced by the high-fat, highly processed environment we are all navigating today.
It's not just about the volume of food you put in your mouth.
Exactly. It's about how the deeply embedded chemical managers in your body react to the specific type of food.
And that realization forces us to view the consequences of our modern diet through a much wider lens.
A completely different perspective.
Because the junk food environment isn't just tricking our brains into wanting to consume more calories. It is actively interacting with and altering our deep metabolic managers in ways we're only just beginning to comprehensively map out.
We're tinkering with systems we don't fully understand.
And honestly, as researchers continue to map it out, the story actually gets quite a bit darker.
It does take a turn here.
Because if we establish that dynorphins manage energy on a cellular metabolic level, we need to bridge the gap back to the behavioral side.
Right back to the brain.
We need to move from the quiet mechanics of metabolism into the loud, destructive realm of addiction.
That's the heavy part.
How do dynorphins, these peptides that manage our cellular furnaces, create that emotional, frantic, practically unstoppable urge to binge?
Well, binge eating is a unique, highly specific, and deeply distressing psychological and behavioral phenomenon.
Right.
It's very different from just, overeating at Thanksgiving because the turkey was good.
Right. It's not just being full.
Clinically, a binge is defined as the overwhelming urge to eat far more than you ever intended in a compressed amount of time.
Okay.
And crucially, it is almost always driven by negative emotional states, stress, or intense mental cravings, rather than any true physiological need for calories.
So it's eating to soothe, not eating to survive.
Exactly.
And dynorphins are right there at the center of that emotional storm.
They are the primary biological drivers of it.
Yeah.
Let's go back to those kappa opioid receptors, the KRs,
The locks in the brain.
the locks clustered in the reward centers. When dynorphins flood the system and bind to those specific KR locks, they heavily influence how rewarding food feels to us.
They turn up the volume on the reward.
They dictate the sheer intensity of the craving.
And this is where the medical terminology used in the research starts to overlap with something much more severe, right?
Yes.
Something that carries a lot of societal weight. The data actually confirms that this exact brain circuitry, the interaction between dynorphins and the kappa opioid receptors in the nucleus accumbens, that is the exact same circuitry that is heavily involved in drug and alcohol addiction.
The identical pathways.
We are not using a metaphor here. We are not making an analogy for dramatic effect. It is the literal, identical biological hardware.
The implications of that overlap are staggering, and we really need to sit with it for a moment.
Let's do that.
Because we use the word addictive so casually in our daily lives.
Oh, totally.
We say, oh, this new television show is so addictive.
Or these chocolate chip cookies are so addictive.
Right. We treat it as a synonym for very enjoyable.
Hmm.
But the hard science is demonstrating that hyperprocessed foods are kicking off a genuine clinical cycle of physiological addiction.
Wow.
It follows the exact same neurological pattern as substance abuse,
Which is?
an intense preoccupying craving, followed by the act of binging, leading inevitably to genuine, measurable, withdrawal-like feelings when the substance is removed.
So modern junk food is acting on the brain identically to addictive narcotics.
Exactly. Identically.
I want to dig into that withdrawal aspect because there was a specific phase of the animal testing that really caught my attention.
The blockade study.
Yes. The researchers decided to intervene. They used specialized pharmacological drugs to physically block these kappa opioid receptors in animals that were already prone to obesity and binge eating.
Right, they covered the locks.
They essentially put a biochemical shield over the KO rocks so the dynorphin keys couldn't get in.
Yep.
And when they blocked the receptors, the binge eating behavior dropped dramatically. The animals stopped gorging.
It worked.
But my question is, and this is what I was wondering when I read it, Did blocking the receptor just physically stop them from feeling the bodily sensation of hunger, or did it do something else on a psychological, emotional level?
That distinction right there is perhaps the most profound revelation in the entire body of research regarding dynorphins.
Really?
Oh, absolutely.
That
Because blocking the dynorphin signals did not just reduce the physical and mechanical act of overeating. By blocking the KORs, the drugs actually calmed the negative emotional state of the animal. It completely alleviated the bad feelings.
it calmed the bad feelings.
Yeah.
It didn't just shrink their appetite, it shrank their stress.
Right?
know.
It physically breaks the cycle of needing the food to feel better, only to feel worse when the food is no longer available.
That is massive.
It represents a massive paradigm shift in how we treat eating disorders and obesity. It means that the intense compulsion to eat junk food during a binge isn't driven entirely by the pleasure of the food itself.
Which is what everyone thinks.
That is a massive misconception. The compulsion is actually driven by the desperate desire to escape the negative emotional withdrawal that occurs when you aren't eating it.
You're running from the pain.
Yes. So by blocking those specific dynorphin receptors, the researchers weren't just treating a hyperactive hunger signal, they were directly treating profound emotional distress.
That is incredibly heavy to process.
It changes everything.
It means that the late-night bag of chips isn't a reward. It's not a treat. It is a temporary, self-administered medication for a painful psychological condition that the chips themselves created in the first place.
The disease and the cure all rolled into one bag.
But observing people in the real world, walking around the office or going out to dinner, it's abundantly clear that not everyone reacts to junk food the exact same way.
No, they definitely don't.
I mean, I have friends who can genuinely open a family-sized bag of chips, eat exactly 3 chips, fold the bag over neatly, put a plastic clip on it, and put it back in the pantry where it will literally sit untouched for a month.
It's infuriating to watch.
To me, and to a lot of people listening, that looks like an actual magic trick. It seems impossible.
It does.
So why do some people get trapped in this intense, dynorphin-driven addiction cycle, while others can just casually walk away from the exact same chemical stimulus?
The research gives us an answer for that, too.
It does, and it lies at the fascinating intersection of these microscopic chemicals and our macroscopic personality traits.
Right. And to understand that difference, we have to look closely at the psychological concept of impulsivity.
Impulsivity. We hear that word a lot, usually in the context of, like, buying things we don't need on Amazon or interrupting people in conversations.
Sure.
But in this neurobiological context, what does it really mean?
Well, in this context, impulsivity is defined as the inherent trait of acting without thinking, or the intense demand for immediate rewards coupled with an inability to delay gratification.
Okay.
It is the failure of the brain's stop systems to override the brain's go system.
The stop systems fail.
Right. And it turns out a baseline level of impulsivity is inextricably linked to food addiction.
So it's a measurable vulnerability.
Exactly. Animal studies have confirmed this link time and time again.
How so?
If you test a group of subjects and identify the ones that naturally display higher levels of impulsivity,
To grab the immediate reward.
yes, the ones that can't wait for a larger reward and always grab the immediate smaller reward, those specific individuals are significantly more likely to engage in rapid, uncontrollable eating binges when exposed to high-calorie food.
They just can't wait.
They simply do not possess the biological infrastructure to delay gratification.
But how does that personality trait connect back to our antagonist? Like, how do dynorphins actually interact with this impulsivity?
This is where it gets really dark.
Because the research explains that dynorphins don't just make you hungry. They actively, chemically dampen the activity in the specific areas of the brain responsible for self-control.
Specifically, they target and suppress the prefrontal cortex.
The prefrontal cortex, which is basically the boss.
It is arguably the most advanced part of the human brain. It sits right behind your forehead.
Okay.
It is your executive command center. It is the region responsible for projecting into the future, weighing complex long-term consequences against short-term gains, and ultimately telling you no.
No, you shouldn't eat that.
Right. No, you really shouldn't have that third slice of cake. You will feel terrible tomorrow, and it ruins your health goals. It is the voice of reason.
Here's where it gets really interesting, because I was trying to think of an analogy for this.
Okay, let's hear it.
Think of the prefrontal cortex as the highly responsible, perfectly rational driver of a fast car.
I like this.
This driver has passed all their tests, they know all the rules of the road, and they know exactly when and where to hit the brakes.
Right.
They see the temptation coming up on the road, the extra cookie, the bag of chips, and they decide, logically, to press the brake pedal to stop you from reaching out and grabbing it.
Makes sense.
But when you have high quantities of dynorphins flooding the system, it acts like a saboteur sneaking under the car in the middle of the night and physically cutting the brake lines.
Oh, wow.
It's not that the responsible driver in your prefrontal cortex doesn't want to stop. The driver sees the cookie, knows it's a bad idea, and is frantically stomping on the brake pedal.
But nothing happens.
Nothing happens. You are telling yourself, don't do it. But the actual mechanical ability to resist the temptation, the chemical signal that translates thought into restraint, has been completely dismantled.
The brakes are gone.
The brakes are completely gone.
That is a perfect, highly accurate analogy for what is actually happening at the synaptic level.
Really?
Yes. The dynorphins literally hyperpolarize the neurons in the prefrontal cortex, making it physically harder for them to fire and send that stop signal.
They chemically disable it.
Exactly. The conscious desire to exert self-control might still be present, which is exactly why we feel the guilt, but the neurological infrastructure required to execute that self-control has been chemically silenced.
That's terrifying.
And as the research clearly points out, this creates a catastrophic perfect storm.
A perfect storm of biology and environment.
Yes, because ultra-processed foods are not natural phenomena. They are meticulously engineered by armies of food scientists to be absolutely perfectly irresistible.
They are built in labs.
They are mathematically optimized for the perfect crunch, the perfect melt-in-your-mouth texture, the exact ratio of salt, sugar, and fat to exploit every single evolutionary vulnerability we possess.
Right.
So you have a highly engineered, irresistible external temptation arriving at the exact neurological moment when the dynorphins have chemically disabled your brain's internal ability to resist.
The perfect storm.
When the dynorphin tide comes in and cuts the brakes, the engineered temptation wins. It's a biological certainty at that point, not a failure of character.
To truly understand how devastating this perfect storm is and why it is so hard to break out of, we need to drive this deep dive down even further, right to the microscopic level.
Into the chemistry.
Exactly.
Okay.
We need to look at the exact neurochemical sequence of what happens the second you start eating a processed snack.
Let's walk through it.
How did dynorphins interact with the other famous brain chemicals we are always hearing about? Let's talk about the chemical tug-of-war happening inside your head during a binge.
Well, to set the stage for that tug-of-war, we first have to talk about dopamine.
Okay, dopamine.
Dopamine is the primary neurotransmitter that everyone universally associates with reward, motivation, and pleasure.
It's the famous feel-good chemical.
Right.
It's what you get from getting a like on social media or winning a hand of blackjack.
Exactly. When you tear open that bag and take that very first bite of a hyper-processed food, the combination of salt, fat, and carbohydrates triggers a massive, instantaneous flood of dopamine into an area of the brain called the nucleus accumbens.
The feel-good hub.
Yes. This unnatural flood of dopamine creates a massive, immediate high. It is a spike of pure reinforcement that screams at your brain, "This is amazing, we need to do this again immediately."
It makes you want more. Instantly.
Instantly.
But the high doesn't last. The second chip never tastes quite as euphoric as the first chip.
Never.
And that is because of our silent antagonist?
Right. This is where the dynorphins activate and add a devastating layer of complexity to the binge.
What do they do?
Well, the brain thrives on homeostasis. It doesn't like massive chaotic spikes of any chemical, even the good ones.
It wants balance.
So in response to the massive dopamine flood, the brain releases dynorphins as a countermeasure.
Oh, I see.
The dynorphins attach to their KR receptors, and they actively, aggressively reduce the further release of dopamine.
They shut it down.
They intentionally pull you down from that peak feel-good state to protect the system from overstimulation.
So the junk food creates the euphoric high, and the dynorphins swoop in like the biochemical fun police to basically shut it down.
The fun police, exactly.
And the literature uses a very specific clinical word for the resulting emotional state that follows.
Dysphoria.
Dysphoria. It is the exact opposite of euphoria.
What does that feel like?
It is a difficult state to describe if you aren't paying attention to it, but it is deeply uncomfortable. It is a mild, lingering negative mood.
Okay.
It is a sense of deep, unplaceable dissatisfaction, irritability, or just feeling fundamentally off or empty.
And what do you instinctively do when you feel dysphoric, empty, and dissatisfied while holding a bag of chips?
You eat more chips. You reach into the bag for another handful. You consume more of the ultra-processed food in a desperate attempt to chase that initial beautiful dopamine hit.
You're chasing the dragon.
You are trying to recreate the high to erase the dysphoria. But the brain is highly adaptive.
Very adaptive.
Over time, as this cycle repeats itself day after day, year after year, the brain adapts in the worst possible way.
It builds a tolerance.
Yes. As the binge eating continues, the negative dysphoric feelings caused by the dynorphins actually ramp up.
They get stronger.
The baseline of stress gets higher. Meanwhile, the positive feel-good effects of the dopamine slow down.
The receptors downregulate.
The high gets weaker.
It is the absolute classic textbook mechanism of tolerance in any addiction model.
Right.
You are continually chasing a neurological reward that feels less and less satisfying, while the chemical punishment for not getting it becomes more and more severe.
That right there, that is the massive aha moment of this entire deep dive.
It really is the core of it.
Because it is a cruel, tragic irony that perfectly explains the frustration of a binge.
Yeah.
Think about it. The more ultra-processed food you eat over time, the less actual joy or pleasure you get from it.
The food literally stops tasting like magic.
Right. But simultaneously, the more miserable and stressed you feel without it.
Yes.
Your brain's entire reward system has been completely inverted by the dynorphins. You are no longer eating because the food tastes amazing.
Not at all.
You're eating entirely to self-medicate the negative, dysphoric mood that the previous bite of food created.
If we connect this to the bigger picture, it is a self-perpetuating cycle of biological misery. And dynorphins are orchestrating this entire symphony.
It's wild.
But the tragedy doesn't stop with dopamine.
Oh, there's more.
Dynorphins are systemic disruptors. The research notes that dynorphins also heavily influence other critical neurotransmitters in the brain, specifically acetylcholine and glutamate.
Acetylcholine and glutamate. Okay, we hear about dopamine and serotonin all the time, but those two are a bit less mainstream. What exactly do they do in the context of eating?
They are absolutely critical.
Yeah.
Acetylcholine is deeply involved in memory formation, learning, and how we process environmental cues.
Okay.
Think about classical conditioning. Acetylcholine is the chemical that logs the sensory details of a reward.
Like the smell of the French fries from down the street?
Exactly.
Yeah.
Or the specific crinkle of the plastic snack bag, or the neon colors of a fast food logo.
Oh, so it builds the association between the environment and the food.
Exactly.
Yeah.
And then you have glutamate. Glutamate is the brain's primary excitatory neurotransmitter.
It's a gas pedal.
It is the ultimate go signal. It is the chemical that takes that memory and drives the intense obsessive craving pathways.
Okay.
It turns a casual memory of a donut into a frantic, immediate need for a donut.
So how do the dynorphins mess with them?
By interacting with acetylcholine and glutamate pathways, dynorphins essentially scramble the communication signals across the entire learning and reward circuit.
They hack the system.
They corrupt the data. They take those environmental cues, the crinkle of the bag, and instead of just triggering a pleasant memory, the dynorphins ensure that the cue triggers a spike of stress and a massive glutamate go signal that overrides everything else.
Wow.
They disrupt the delicate, rational balance between wanting food and having the cognitive ability to manage and dismiss those cravings.
Which leads to what?
It leads to a total systemic loss of behavioral control.
It is a bleak, incredibly bleak chemical trap.
It sounds hopeless, I know.
It does. When you lay it out like that, detailing the dopamine crashes, the corrupted memory signals, and the completely disabled prefrontal cortex, it feels like we are completely at the mercy of a biological system that is being intentionally weaponized against us by the modern food industry.
It definitely feels that way.
It feels hopeless. But after outlining all of this microscopic darkness, the scientific community isn't just throwing its hands up.
No, they are not.
There is a pivot in the research. The researchers ask the vital question: how can science use this exact granular knowledge to actually help us?
Right.
If we have finally mapped the lock, can we build a key? Let's talk about the horizon. What are the treatments?
Well, there is absolutely immense hope on the horizon, and it lies in the rapidly advancing realm of targeted pharmacology.
Okay. Drugs.
Yes. Now that we understand that the kappa opioid receptor is the linchpin of this dysphoric cycle, drug developers are aggressively focusing on pharmacological blockades of those KORs,
So we are talking about developing drugs that act like tiny, perfectly shaped shields.
basically.
They float through the brain, find the KOR locks, and cover them up so the dynorphin keys can't dock and trigger the dysphoria.
Precisely. They are KR antagonists. And in the animal studies we discussed earlier, this approach is proving to be a highly promising, incredibly effective real-world solution.
It's actually working.
It is. When these antagonist drugs successfully block the receptors, they don't just act as a brute force appetite suppressant, like older diet pills.
Right. Older diet pills just made you feel wired or sick.
Exactly. These new drugs seem to actively, gently restore that healthier reward balance we were just talking about.
Oh, wow.
They stop the dynorphin-induced dysphoria, which removes the desperate need to self-medicate with junk food.
It stops the pain, so you don't need the bandage.
Perfectly said.
But the research also makes a crucial, very nuanced point about why these new treatments won't just be a blanket prescription handed out to every single person who wants to lose 5 pounds.
Right, it's not a magic pill for everyone.
Because we talked earlier about why some people can eat one chip and walk away while others eat the whole bag. Aside from baseline impulsivity, it comes down to the foundational blueprint of our bodies, our genetics.
This is a vital point for the future of medicine. The genetic mapping in these studies highlights that there are massive, significant genetic differences in how dynorphins and the KRs are expressed in different individuals.
Meaning, just based on the genes I inherited from my parents, my brain might literally, physically possess millions more of these KOR docking stations than your brain does.
Exactly.
Or my body might naturally produce a massive tidal wave of dynorphins in response to a cookie, whereas your body only produces a tiny, manageable splash.
Precisely. The biological variance from person to person is huge.
That makes so much sense.
Some people have a genetic mutation that makes their KRs highly sensitive. Others have receptors that are relatively muted.
Right.
And this profound genetic variance perfectly, elegantly explains why some people struggle so deeply and chronically with food addiction, while others navigate the modern food environment with zero friction.
It's just hardware.
It proves, once and for all, that chronic overeating is not a difference in moral character. It is a fundamental difference in biological hardware.
That is so freeing to hear.
Yeah.
Like, really?
It is. And because of this variance, the metabolic treatments of the future will need to be highly tailored to the individual's specific genetic makeup.
Precision medicine.
Yes, we are rapidly moving away from the archaic, one-size-fits-all diet culture where everyone is told to just eat chicken and broccoli and suffer.
So what does this all mean? Let's bring this all the way back to you, the listener, right now in your kitchen.
Yes.
It means that the long, punishing era of relying solely on raw willpower and generic restrictive diet plans is ending.
Thank goodness.
The scientific community is officially completely removing willpower from the equation. Your struggles are a matter of biological variance.
Which is incredible to finally acknowledge.
And the future of treating compulsive eating isn't going to be about desperately trying to suppress your appetite with dangerous stimulants or starving yourself.
No.
It is going to be about precision medicine. It will be about individualized, genetically mapped treatments designed to restore a healthy baseline chemical reward balance in your specific brain.
Targeting the exact neuropathways that junk food has been exploiting for decades.
And the research certainly doesn't stop with simply blocking the receptors. Looking ahead, the scientific community is fiercely focused on understanding the lifelong developmental impact of ultra-processed diets on these human dynorphin systems.
Right.
What do you mean by developmental impact, though?
They are trying to map out exactly how long-term exposure to these engineered foods, especially during childhood and adolescence when the brain is still forming.
Yeah, kids.
How it permanently alters a person's baseline obesity risk and their inherent impulsivity.
That's a scary thought.
Does eating a high-fat, hyper-processed diet as a teenager permanently upregulate your dynorphin production for the rest of your life?
So it could change your baseline forever.
Exactly. Broadening our knowledge of how dynorphins chronically interact with dopamine, glutamate, and acetylcholine over a lifespan will paint the full picture needed to develop truly smart, highly effective, and perhaps even preventative interventions.
It is an incredible paradigm-shifting journey we've been on today. To summarize everything we've unpacked, we have completely reframed the conversation around junk food and overeating. We've learned that dynorphins are far, far more than just simple, isolated hunger hormones.
Much more.
They are incredibly complex managers of our cellular energy that can completely derail our metabolism.
They hoard fat,
Right. They are potent dopamine suppressors that actively cause negative dysphoric moods, forcing us to eat just to feel normal.
The fun police.
And they are the chemical scissors that sneak in and cut the brake lines of our self-control in the prefrontal cortex.
Yeah.
And tragically, they are easily, almost effortlessly, manipulated by the highly engineered, ultra-processed foods that fill every single aisle of our grocery store shelves today.
Which brings us to a final underlying reality of all this research. This raises a very important question, a final thought to really mull over as we conclude today's deep dive.
Let's hear it.
We established earlier that dynorphins act as this ancient, deeply embedded evolutionary backup system.
The emergency starvation protocol.
They are a biological failsafe guaranteed to force feeding behavior in severe life-or-death famine scenarios.
Right.
And we also established that stopping the intake of ultra-processed foods triggers the exact same emotional withdrawal as narcotics, driven by these very same dynorphins screaming that something is wrong.
Right.
So, if our modern, highly processed diet is chronically, artificially triggering this specific emergency backup system day after day,
Yeah.
are our brains fundamentally misinterpreting a simple, casual trip to the fast food drive-thru as a literal life-or-death survival event?
Wow.
Are we essentially tricking our deepest, most ancient biology into believing we are starving to death every single time we eat a potato chip?
Because the brain thinks it's saving us.
The system thinks it is saving us from a famine that doesn't actually exist. And if that is true, how can we consciously, rationally outsmart a brain that genuinely chemically believes it is just trying to save our lives?
That is a staggering, profound thought to walk away with. Your brain literally thinks the drive-thru is a desperate rescue mission from starvation.
It really does.
Thank you so much for joining us on this deep dive. The next time you find yourself standing in the kitchen, staring down an empty bag of snacks late at night, I want you to actively remember this conversation.
Yes.
I want you to look at that intense craving through the objective lens of chemistry. Look at it through the lens of ancient hunter-gatherer survival systems, kappa opioid receptors, and dopamine crashes.
Look at it through the lens of biology, not guilt.
Exactly. You are not weak. You are just working with an ancient biological remote control that the modern world has basically hacked.
Well said.
We will see you on the next deep dive.